All right, so we are now in section 1.3, and hopefully by the end of this section, you're going to start to see why I begin with the study of vectors in a linear algebra class. Because what we're going to do now is we're going to start to think about how a vector would be described or represented in the form of a matrix. So, for example, notice that, although you're not told this yet, but what you're given here, this is a 2 by, there's two rows, 1 column. So this is a 2 by 1 matrix, and this is a 2 by 1 matrix. And what I'm going to be telling you in just a second is that this is what we call a column vector. Okay? In fact, and I'll write this in another page, but in any matrix, any n by 1 matrix is a vector, a column vector. Now, let's start with just some basics. As you recall, if you want to scale a vector, so let's just assume that if you want, so let's start here with 4u. That just translates into, we're going to take 4, and that's going to be scaled into this 2 by 1 matrix. And it's pretty simple. It's pretty simple to scale, just like it's simple to scale a vector, it's simple to scale a matrix. It's just every entry inside the matrix is going to get multiplied by 4. So the result is 4 times 1 is 4, and 4 times negative 2 is negative 8. So that's the result. Okay, so negative 3v. I think you can kind of see where I'm going with this. So v is the matrix 2, negative 5. And the result of that is going to be negative 3 times 2 is negative 6, and negative 3 times negative 5 is positive 15. Now, do you recall for a second that although when we did dot products, a vector times a vector and using a dot product was actually a scalar. But as you recall, that a scalar times a vector was still a vector. And what you're noticing here is that when you scale a matrix, notice that this was we started with a 2 by 1 and we finished with a 2 by 1. We started with a 2 by 1, we finished with a 2 by 1. Okay. Finally, they want us to take 4u and we're going to combine it with negative 3v. So I'm going to erase everything. Well, I'm going to erase everything so I have some room. But we've already done 4u, and we've already done negative 3v. So 4u was 4, negative 8, and negative 3v was negative 6 and 15, I believe. Okay, so when it comes to matrices, if you want to add matrices, you can only add matrices of the same dimension, right? So you can add a 2 by 2 matrix to another 2 by 2 matrix, not a problem. But you cannot add a 2 by 2 matrix to a 3 by 3 matrix, or a 2 by 2 matrix to a 2 by 3 matrix. They have to be the same order. But since this is a 2 by 1 and this is a 2 by 1, then we can proceed to add these matrices. And we do so by just just, you know, row by row. So this is going to be 4 combined with -6 gets us at -2. And this is going to be -8 combined with a +15, which is going to give us a +7. And this is the result. Okay? So again, just like in the vector lessons, one vector plus another vector, that was called the resultant vector. And what I'm telling you now is this is the way you would write a vector in a matrix. And I will touch up on that just a little bit more right now. So when it comes to vectors, we are, at least your physics, engineering classes, you're used to seeing vectors written as directed line segments, right, with the arrowheads. But these arrows, although they do serve as an aid in interpreting, right, like it's easy to see the direction of your vector, but they do not have any significance. So you can write a vector as a directed line segment, or you can write that same vector as just a point. Now, of course, we are assuming that, right, with any vector you have an initial and a terminal. The initial point is at the origin. So if your initial point is at the origin, then do you see how you can represent the entirety of the vector by just its terminal? Okay, so what I want to make sure you understand is that column vectors is any n by 1 matrix. Okay? Meaning it doesn't matter how many rows, it can only have one column, right? Like you can have 4 rows but one column. That's still a vector. Now, so I'll just kind of write it. So this is what we mean, just one column, but it doesn't matter how many rows. So this is a column vector. Now, the next question is, well, we understand what a scalar is. How would you write a scalar, right? A scalar in matrix form, right? So a scalar can be written as a matrix with a single entry. All right, or a 1 by 1 matrix is a scalar. Okay, so a 1 by 1 matrix, one row, one column, is the equivalent of a scalar, right? It's the analog of a scalar in matrix form. Now, equal vectors, to be able to say vectors are equivalent, so if and only if the corresponding entries are the same. So, for example, let's just say 4, 7 does not equal 7, 4. These are not, this is a vector, but they are not equal vectors, because in order to have an equality of vectors, if you have a 4 here, you would have to have a 4 here. If you have a 7 here, you'd have to have a 7 here. That should make sense if you want to think IJ notation. If this is 4i, then you should have 4i here, right, in order to have an equivalent vector, not 7i. Okay. Now, I want to kind of talk about the dimension for just a second. So, if you are in 2 dimensions, right, like a plane, we refer to that as R2. 3 dimensions is R3. Okay, so we'll just kind of keep that in mind. So clearly, these vectors are in 2 dimensions. Okay, but we'll come back to the dimension part in just a second. Just if you hear me talk about R2 or R3, just understand that either I'm talking about space or I'm talking about a plane, right? Some 2-dimensional plane. Now, let me pose a question. So let's assume that I give you some vector v and some scalar c. So some vector v and some scalar c, and let's go ahead and make the stipulation that these are non-zero, right? So in other words, the scalar is not 0 and the vector is not a 0 vector. So if I give you some vector, some non-zero vector and some non-zero scalar, my question to you, which you obviously can't answer, but my question to you is, geometrically, what does this look like, right? Just the product of a non-zero scalar by a non-zero vector. Geometrically, what does that look like? Notice I'm pausing. So what would the graph of this look like? Well, although maybe I can use this little graph up here to kind of serve as an aid. So forget about the rest of this. I'm only going to use v. Now, if I scale vector v, well, if I scale it, I could make vector v longer, right? I could double it, triple it, 3v, 4v, 2v. I could also make vector v smaller, right? Half of v, a third of v. I could even make that scalar negative, right? And flip the direction of v. So are you with me when I say that geometrically that is the equivalent of a line, right? By just changing my scalar, I can just increase, decrease, change direction of vector v. In other words, if I were to graph all of these possibilities, that would be a line. I think that makes sense. So let me see if we can start to let's get good with this, right? So I'm going to assume that I give you the point 4, 3. All right, so let's go over 4, up 3. So over 4, up 3. So right here, 4, 3. Okay. Now, you recall, and what meant most of you engineering, science majors, the majority of the vectors that you encounter in engineering, in physics, etc., all have I or J notations, right? Now, I didn't, I didn't learn vectors and IJ notation or practice them as much as many of you have, but what I want to make sure you understand is, hey, that's IJ notation is nice, but that I represents a vector, right? That I literally represents a vector. Well, I'll first write it as, let me go ahead and write it like this. So that I represents the following vector. Right, I'm sorry, I screwed that up. Have one first. It's 1, 0. In other words, whenever you have I or J notation, the I is a unit vector, length of 1, and the direction, that part is along the x-axis, right, horizontal. Whereas the J component, tells you about the direction vertically, but it too, the J is a vector, and it's a vector in the direction of 0, 1. So it's a vector of length 1 in the direction of the y-axis. So to make sure you understand, now I'm not going to use the I notation, J notation for right now. I'm going to go ahead and let's call this vector 1, 0, let's call that vector V. And let's call this 0, 1, let's call that vector U. Okay, very important what's coming up. What's coming up is what we're going to call a linear combination. And it's critical. It's critical that you grab this information. Okay, so here's the game. Are you ready? Here's the game. So let's pretend that I give you two vectors, these vectors here, U and V, and I give you two scalars, C sub 1, C sub 2. The scalars can be any non-zero numbers. Now, a linear combination would mean that you have your first vector, vector V, scaled at C sub 1, plus your vector U scaled at, say, C sub 2. The game is as follows. If I give you these two vectors and two scalars, what points can you reach in the plane? For example, can you reach 4, 3? What am I trying to say? I'm simply saying, hey, is there a way for you to pick some scalar? Is there a way for you to combine your vectors such that the result is the vector 4, 3? Right? So a linear combination, you have addition and you have scaling. So can you add and scale? Okay. Now, when I first gave you the point 4, 3, please stay with me. When you first learn points, you think of them as plotting, right? Over 4, up 3. But listen, plotting points is actually should be thought of as linear combinations. So let's go ahead and do this for a second. So I'm gonna insert. I'll leave C sub 1 alone. I'm going to go ahead and insert V, 1, 0. And I'll leave C sub 2 alone for now. And I'm going to go ahead and insert 0, 1. Now, the question that I had was, the game that you're playing, can you pick a scalar, two scalars, such that when everything is done, you arrive at the vector for 3. Huh. Well, we're gonna come back to this, but let me go ahead and tell you. If you chose 4, right? If you chose 4 for C sub 1, and you chose 3 for C sub 2, interestingly enough, let's do some arithmetic here. So 4 times 1 is 4. 4 times 0 is 0. 3 times 0 is 0. 3 times 1 is 3. And finally, you can add 4 plus 0 is 4. 0 plus 3 is 3. This is amazingly interesting. You can arrive using these 2 vectors. You can arrive at any point in all of R2. Right? In other words, I can reach this point right here by just choosing scalars and then scaling them to these vectors. Right? Just the linear combination of those vectors and scalars. I can reach any point that I want in all of R2. What this means for us, and we'll come back to this idea of base vectors, bases. We are so used to, when we plot points, first off, we're used to our X and Y coordinates being nicely intersected at perpendicular lines. That doesn't have to be the case, right? You can, I will show you, I won't do it today, but I'll show you. You can have lines that are skewed so that you, and still think about plotting points. But the main takeaway from this little tutorial here is I want you to understand the idea of span. Very important, span. So the span of a linear combination of 2 vectors, I'm going to say it again. So the linear combination of 2 vectors, that just means 2 vectors, the sum of 2 vectors and 2 scalars, right? So this is a linear combination. Now, what I'm trying to tell you is the span of this linear combination is indeed all the vectors that you can reach from that linear combination. Now, we like I and J. We like this 1, 0, 0, 1 because it allows us to plot points over 4, up 3, and the linear combination allows us to reach any point in all of R2. But what I want you to understand is we'll have to come back to this in another video, but we want to start asking questions like, hey, if I were given 2 other vectors, right, 2 scalars and 2 other vectors, can I still reach every point in R2? Or maybe I can only reach a certain part of R2. Can you imagine? What if you could only reach the points in quadrant 4? Well, that is where we're going to be going. Again, the takeaway from this video is, what is a linear combination? Well, it's the sum of 2 vectors that have both been scaled by some non-zero scalar, right? So the sum of 2 non-zero vectors both scaled by non-zero scalars. That's a linear combination. The span of a linear combination is just what's the reach? What vectors can you reach through the linear combination? Can you like we did here, we see how we were able to get to 4, 3, right? If we couldn't, if there were no way to through linear combinations, if there was no way to get to 4, 3, then we would say 4, 3 is not in the span of that linear combination. But of course, since we can arrive at 4, 3, then we say that 4, 3 is in the span of this linear combination. Okay, so that will go ahead and take us through the end of this video, and I will see you soon.